So we're going to look at a YAG laser rangefinder that was used to be on a military aircraft, and now it wound up being surplus equipment, and it was picked up at a university, and now it's being used at the university. So we're going to take a look at this. We have a wavelength of 1064. It's repetitive pulse. We have an energy per pulse of 30 millijoules, pulse duration of 5 nanoseconds, a pulse repetition rate of 10 hertz, and we'll be using the ANSI default exposure duration of 10 seconds. We have 1/e squared, circular Gaussian, and now we've come up with a beam diameter of 16.93 millimeters. Now, we may want to ask where that came from. And based on a previous discussion, we know that if we take the output aperture, now the beam expander being used on this has an output aperture of 25.4 millimeters. And so if we take that output aperture and we divide it by 1.5, that will tell us the worst case beam diameter that we should use through that beam expander, okay? And that's based off of what we call the 99% criteria that says that 99% of the beam is going to be passing the clear aperture. We're going to clip 1%. If we clip any more, the power gets dumped into the diffraction rings. We start losing power faster than we're creating a beam that can propagate further, so that this diameter, by calculating it using the 25.4 divided by 1.5, this gives us a beam diameter that gives us the highest irradiance at a distance. Okay, and that's what we're concerned with the beam expander. So that's how we came up with this diameter. Okay, and then m squared is 1.1. This is now. We have said when you don't know, it's 1. Now, in this case, we have somehow been given the information that it was 1.1, but if I did not know, or we didn't know the m squared, I wouldn't necessarily assume 1, because these rangefinders aren't going to be close to 1. They're going to be over probably about 1.2, 1.3, something like that. So an m squared of 1.1 is a realistic m squared to be using in this case, and it calculates a divergence. Look at this, at 88 microradians, and that's because we have this big beam here. So this beam is not going to get large or over distance very quickly. That is a very low divergence. But of course then, for a rangefinder, that's exactly why we're using an expander. We're trying to range something that is kilometers away, and we want to only paint that target. We don't want to be looking at ranges of a number of different things. So we want to just paint the target, and so we want to keep that beam small, and that's what expanders do for us. Okay. Now, we will assume that our observer at the moment is a half a meter away. There's no change in the beam diameter at observer range, of course, not using this small of a divergence. This gives us an OD at observer range of 4.053. The worst case is 4.591. What's the difference here? Well, it's the power being transmitted through the limiting aperture, and in this case it's only 29% of the 30 millijoules. If we take a look at that, the energy transmitted is about 8.7 millijoules is being transmitted through the limiting aperture, and of course that's what we're using to determine the irradiance of the laser. And we're still looking at average irradiance because we're looking at the average power that is passing. And even though we don't tell you that right here, where you can get some of this is laser calculated values, we can see that the average power from these conditions is 300 milliwatts. The peak power, look at this, is 6 megawatts. So this has quite a pulse, all right? This is what we're more concerned with, and we can tell that from the MPEs. We have two rules here, and the Rule 1 MPE is about the pulse duration. Okay, so we can see that it's the rule 1, the pulse duration or exposure duration associated with the pulse that's driving this analysis. You can see that the MPE for based on the average power is a couple of orders of magnitude off. So of course the rule 1 is the more restrictive. If we want to change this into watts, we can take a look at it in terms of watts. And of course that's where the MPE over here is being reported in watts per square centimeter, and over here we've changed it to watts per square centimeter, or radians, and we can put it back into radiant exposure. All right, and just to be clear, these are both in what we call single pulse MPEs. The rule 2 has been converted from an average power using, when we look up the MPE in the table, we have to divide that MPE, the rule 2 MPE, based on this exposure duration by the number of pulses in the exposure, so that we take the MPE that we get out of the table and we associate what part of that MPE, the energy or power, is associated with a single pulse, and in this case it would be energy, is associated with one pulse, and then we can compare these two rules. We have to always remember in our comparisons that we have to compare apples to apples, so we can convert the rule 2 MPE to a single pulse MPE so we can compare it to rule 1, and that's what has been done here. If we wanted to do it in average power, that's what is happening here, and you would multiply, you would leave this and multiply this by the repetition rate, and that's how we move, put this back, from 2 times 10 to the 2 times 10 to the minus 6 joules per square centimeter to 2 times 10 to the minus 5th watts per square centimeter is multiplying this by the repetition rate of 10 hertz. All right, I think hopefully that was understandable, and that I didn't make too big of a mess out of that. Anyway, let's move on. All right, so let's take a look at the diffuse reflection hazard. We have a spectral reflectivity of 100%, viewing angle of 0. These are our worst case. Our beam on target, though, is huge, all right? It's almost 17 millimeters. Our observer range is quarter of a meter, 600 seconds exposure duration, and at this range, of course, this is an extended source, but look at this angle subtended, almost 48 milliradians. Okay, so we have a high C sub E, which is really making this MPE for the diffuse reflection much less restrictive than the point source MPE being used over here. So that's the reason we don't have any NHC, and there's no OD at observer range. And then, of course, we take a look at the times skin MPE here, and there's no hazard for the diffuse reflection. Let me move over here to the MPEs over here, where I had been. We were sort of looking at these when we were talking about the rules. So the ocular MPE is 2 times 10 to the minus 5th watts per square centimeter. The skin MPE is 1 watt per square centimeter. And we'll notice that the times skin MPE is less than 1. Wow. Yeah, that's because of the big beam. We're looking at the transmission through the limiting aperture of the skin, which is only 3.5 millimeters. Now you'd say that, well, that's going to make a big difference, but remember, you're averaging that over the area of this, and this area is much smaller than what you're thinking about the area in the limiting aperture of the eye. Let's take a look at that. Look at the difference in these. So just because you have a smaller limiting aperture doesn't necessarily mean, and it's passing less power, doesn't necessarily mean it'll generate a lower irradiance than a larger limiting aperture that's passing more power, but that larger limiting aperture has a larger area, okay? And area has more to do with irradiance than anything else, because those areas are squared, and so if you have a small area compared to a large area, you'll notice that that large area gives you a much lower value in irradiance, okay? But I did want to point that out, that these are different, okay, and that you do have a small area here, so you are, but you're only transmitting a very small fraction of the power through the limiting aperture for the skin. Okay, so that's the reason the time skin MPE is 1 or less than 1, and no skin hazard for the intrabeam exposure to this laser, also for a 10-second exposure. Let's look at the NOHD. Wow, the NOHD is huge here. You're looking at 22 kilometers, which is kind of typical for a rangefinder, right? I mean, it's got to range find over several kilometers. Right. Now, this is a little misleading because it is, we are propagating the beam right now in what we consider to be a vacuum. All right, so we haven't added any atmospheric attenuation, which we'll do in just a moment. The NSHD, nominal skin hazard distance, is 0. That's what we would expect. Since we looking at our time skin MPE is less than 1, we don't expect to have a nominal skin hazard distance, and we don't. All right. Now there is one thing I want to point out. We did say that by dividing the the output aperture of the beam expander by 1.5, so that's 25.4 millimeters divided by 1.5, that gives us our beam diameter. Okay, that is the 99% criteria. So we're kind of expecting that with a 16.93 millimeter beam diameter passing through a 25.4 millimeter, we would expect about 99% of the power to be passing. But how do we check that? Let me show you real quick. We're going to come up here and, oh, you know what? Before I do that, I need to turn on optically aided viewing. So I'm going to do that. And of course, when we do, this goes way up. This goes to 132 meters. That's because our limiting aperture has changed to 50 millimeters, because with optically aided viewing, we're looking at that because with a rangefinder, it's very possible that somebody downrange might be turned around looking back towards this rangefinder with a pair of binoculars. And we're talking about a sort of a standard pair of binoculars with a 50 millimeter aperture on it. So that's why this the NOHD has gotten so much larger. All right, but let me go up here. I'm going to go to miscellaneous, extended features, and I'm going to go to optically aided viewing, limiting aperture, transmission. Okay, and I'm going to click that, and I get this box. So what I'm going to do, I'm going to change this aperture to 25.4 millimeters, and I'm going to change the transmission through the optics. Remember, when we click on optically aided viewing, it depends on what wavelength range we're in. There's a default, and you can look at table 9 in the ANSI standard, that says, yeah, because you're in the near IR and binoculars are coded for visible light, we only expect about 70% of the light to transmit through those binoculars, and that's what we're showing here. This is the ANSI default. So what we're going to do is we're going to change this to 100%. We've now set our aperture that we're seeing over here to 25.4. We're going to say OK to that. And what we get when we do that is the transmission through the limiting aperture of 25.4, and you can see that's about 99%. Okay, so we've verified that a Gaussian beam at 1.5 or 0.67% of the output aperture does in fact result in a transmission through that aperture of 99%. Okay, so let me go back. And I'm going to reset the extended. I'm going to reset this back to the defaults. Okay, and we'll say OK, and everything kind of goes back. So now you can see where this shows up at the transmission through the limiting aperture of only 70%. That's because it's the ANSI default for a pair of binoculars coated in the visible passing infrared light. We kind of default to 70%. But now you can see how you can change that. And you can see how optically aided viewing affects the results here. Okay? All right. What happens if we add some atmospheric attenuation here? First, let's turn this off just for the grins of it again, and so we can look at it separately. And I believe in the example, let's use 6 times 10 to the minus 7th reciprocal centimeters. That's something between a very clear and standard clear day. So 6e to the minus 7th. And what you want to do is watch the NOHD right here. And we'll enter that, and the NOHD does, in fact, go down a bit. It drops down to about 14 kilometers, right? And so it depends on how much atmospheric attenuation we add into that as to how it will affect the NOHD. And then, of course, we expect this to go back up if we turn on optically aided viewing, okay? And it does go up a bit. So, all right. So I think that kind of covers optically aided viewing, what we talk about there. Atmospheric attenuation, we'll set that back to 0, and we're kind of back to where we originally started with this example. Okay, I think we've covered everything pretty much. The one thing I didn't really cover, I was starting to look at this where I said, well, you have 300 milliwatts of average power. Not a lot of average power, right? And that's because, well, you don't have a high pulse rate. Right. A lot of peak power, so this is pulse has quite a pop to it if it's in a small enough beam. But we also report the duty cycle. In other words, this is the on time versus the off time of the beam. So the pulse is the on time, and in this case, we're running 10 pulses per second, but each pulse is only on for 5 nanoseconds. So 10 times 5 nanoseconds is the total on time per second, and then for the rest of the time, the beam is off, and that's what's reported here. It's a very low duty cycle. It's 5 times 10 to the minus 6% duty cycle. Okay, but yeah, you can get that information down here from the laser calculated values. All right, I think, I want to change this back. There we go, to watts per square centimeter. We do, yeah, I guess I could mention that while I'm here. We can express pulse radiant exposure and average radiant exposure if we want to. Most of the time we're reporting irradiance, but we can select this by and go to radiant exposure for the calculation of the laser, either irradiance or radiant exposure. Okay, there we go. All right, I think that's about it.